Let's recap the decision tree classifier. The way it works is we have all our training observations in one node, and the algorithm goes about choosing what is the best question to ask to best separate the points. And the metric for separation, separating the points, can be either the Gini metric or the entropy metric. We perform the split, we create two spaces, then we repeat the process on the two resulting nodes. It continues on until we reach a termination criteria. Now let's consider regression. How can we take the decision tree model and use it for regression? Well, it's going to have a very similar process. We have all the training points in one node in our entire space, and then we go about asking what is a good question to separate our points. But now we don't have classes. Our observations don't belong in classes. So how do we define best separate the points? Well, we understand that each of the points, all our training examples, have a y value, the target value, the labels. And one way we can go to best separate the points is that we want to create two nodes in which the resulting variance, overall variance, has dropped. In mathematics, we understand that variance is a measure of spread, the variability of a value. So for all our training points, we can calculate the variance. That tells us how much does the y label spread out, how much does it varies across our training set. Such that now there's a question that I'm looking for, a criteria to split my space, in which all points go in this way and all points that meet the criteria go to this other space here. When I create those two spaces, I can calculate the resulting variance in each space, in each node. So I take the left node, I can calculate the variance, go in the right node and calculate the variance there. And I can measure the overall drop in variability. So what I want to do now is I want to create a space, create a division between my points, create a split in my root node such that there's an overall drop in the variance with when I create these two nodes. So I'm looking to create an overall drop in variance. So we can write that overall drop in variance in this equation here. So sigma squared represents the variance, and the subscript L and R represent node left and node right, whatever you call node left and right, the two resulting nodes from the split. And the term in parentheses is a relative fraction. So n of L is going to tell you the number of points, the number of training points that reside in the left node, and n of R is going to tell you the number of points that reside in the right node. So this will tell us what fraction of the training points goes to the left and what fraction of the training points go to the right. And that's going to be used as a weight when we calculate the overall drop in the variance by performing a split. Let's examine using a decision tree model for regression. So we're going to import the decision tree regressor model. We'll import the famous California housing data set. Let's go ahead and get that data set. Let's go ahead and construct our tree and max depth of 3. In this case, pass X and Y. Let's go ahead and visualize our tree to understand how it works, how it looks like. And this is a resulting tree structure. Notice one thing you might want to ask yourself is, for a given depth of tree, what is the max number of terminal nodes, leaves? So depth 1 we have 2, in depth 4 we have 4, and in depth 8 we have, in depth 3 we have 8. So the max number of nodes in a depth is going to be 2 to the depth of that layer. Makes sense because we have a binary recursive process. each node that we create, we further split into 2. So notice now, at a depth of 3, we have a total of 8 nodes at the deepest layer. So looking at this here, let's go ahead and look at our tree model. Once again, we have something that resembles what we had before. We have an upside down tree. So this is our root node here. And the question I decided to ask was, is the median income less than equal to 5? Roughly 5. Let's point out what you might be wondering, what is MSE? So samples is going to refer to what we had before. Samples tells you how many training points reside in this node. The entire California housing dataset has over 20,000 observations. So we have 20,000 samples here. Value is going to be the mean value of all the training points that reside in this node. MSE is going to be the mean square root error. If we go about assuming, we go about predicting that all the training points that reside in this node have this mean value here. So if I were to write that down, let's go and write down the equation for the mean square root error. So we have the summation, 1 over all the training examples. So we have y, that's a true value there. So this is a true value. Let's sum up for all observations. So this is our predictive value squared. And for decision tree regressors, we always predict the mean value. So in other words, in this case here, we're going to predict a mean value of all the training points, in this case 2.069, for all the observations. So they all have the same value. So I'm going to write that equation as simply y hat I of j squared. Now what does this term here resemble? What does this equation resemble here? What does this term resemble? So we have the summation of 1 over n of y bar minus y of j squared. Well, this resembles the variance. Remember, the equation for variance is simply the summation of x bar minus x of I or j, whatever index you use. So this term here represents the variance, the variability. Okay, so we're going to perform the split. So this is the resulting points here. So resulting 2 nodes. So we sum them across. We have a conservation of nodes. A conservation of training points. We further apply the splitting process. What's the best question to ask? In this case, we're going to use the median income once again to split our space, create two resulting nodes that's going to overall have a greatest drop in variability from its parent node. And then we have all these final nodes here. So these are all leaves, our terminal nodes. And the way you make a prediction using this model is very similar to how we did before. We start with the very top at the root, and you simply, with that observation, you simply go through this space, asking these questions and answering true or false, and see what node your observation lies in. So if our observation lies in this node here, then the value that we predict for that observation is going to be the mean of all the values, all the y values for the training observations. So this node here is made up of 1,954 training points, and its mean value of all those training points is 2.79. So any observation that resides in this node here, we're always going to predict 2.79. If an observation that we use to make a prediction, if it lies in the, let's say, this node here, then we predict 2.563 because that is the mean value of all 1,787 training points that reside in this node. So given the way we make predictions in decision tree regressors, and that we have a max depth of 3, so we have a total of 8 nodes in our last layer, our deepest layer, how many distinct values will this model predict? How many distinct values will we get from this model, given the fact that we have a depth of 3, a max depth of 3? Since we have a max depth of 3, we're going to have a total of 8 nodes at the deepest level. So we have 8 leaves here. So we're going to have a total of 8 distinct values we're going to predict. So one way to view what we're doing with decision trees in general is that we're creating bins. We're creating bins where an observation could lie in. Depending on where that bin the observation lies in, we predict the value for that bin. Now, a couple things I want to point out here that might be a little bit weird is if we look at this node here. Remember what I said, that it's going to perform a split to create the greatest reduction in variability from the parent node. So in other words, you can measure the variability, the variance in this node, calculate the variance in this node, the variance in this node, sum their weighted contributions, then there'll be an overall drop, an overall reduction. What might be confusing is that you can look at something like the mean squared error, which we understand is a measure of variance, is greater than before. So this this child node has a greater variance than the previous node, the node it was derived from. But if we go and look at it, to keep in mind, remember there's a weighted, what we do is we do a weighted variance drop. And this node its variance has dropped. So we go and do the weight contributions, we will see that yes, the overall variance did drop when we perform the split.